Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is hydraulics. You may be asking yourself after going through these first series of lectures, what have I learned? Well, you'd be surprised you've actually learned quite a lot. Here is an example that's going to walk us through basically everything we've learned in this first week. Okay, so here we've got a system, and first task for you is to just identify what these symbols are. So first one right here, that's our reservoir. This is a pump. In between the pressure and the tank is our pressure relief valve. This is a flow meter. Pressure gauge. This right here is a directional control valve. And let's talk a little bit more about the directional control valve. It looks like it is spring-centered. It's a closed center in the center position. It is 3-position, 4-way. What are the ways? P, T, A, and B. And it is manually activated. And then we've got a double acting cylinder, and it looks like it's pushing a weight, whatever that is. Okay, so those are just some schematics. And now that we've identified the schematic symbols, the second question to you is, what does this thing do? Okay, so what does this thing do? Based off the schematics, what you've seen so far, basically our pump is taking fluid from a reservoir, pressurized flow. It's going through our flow meter, which is going to read it, and it's going to stop right there because the closed position. Basically, this is a confined fluid under pressure, and the pump is going to keep on pumping and keep on pumping, and pressure is going to rise, and we're going to see our pressure gauge rise from 0 till it reaches the setting for the pressure relief valve, and let's say it's set at 900 psi, at which point it opens up and starts dumping that flow to the tank. Okay, so now we go ahead and put this thing to the straight through position. So the straight through position is this guy right here. Basically, pressurized flow is going to go through here, and it is going to enter the cap end of the cylinder. But now we've got a weight on this thing here, and the pump is going to keep on providing flow, and once it reaches the maximum of this space, this volume here, it's a confined fluid under pressure, and pressure is going to rise and rise and rise until the pressure requirement required to move this weight, whatever it may be, let's pretend it's 4,000 pounds. So the pressure acting on the area of the cap end of that cylinder is going to increase, because this area here, it's going to increase until the force generated by that pressure on that area moves that particular object, and the cylinder is going to extend. Pretty good so far. On the opposite side, as that cylinder extends, this rod end is going to push out and going to take this flow right here back to the tank. Pretty good so far. Now what happens when we've reached the limits of our travel here? Basically, the cylinder has bottomed out and pressurized fluid in this area, just enough pressure to get that guy moving. Basically, it's finally reached the limits of its travel. Let's say it's 24 inches. And cylinder bottoms out, and now the pressure inside that cap end rises and rises and rises until, again, we're still in the straight through position, it exceeds the pressure for the pressure relief valve, and it starts dumping to the tank. Okay, again, what's the function of the pressure relief valve? It's designed to limit maximum pressures. Okay, so let's say example was 900 psi. Pressure rises to 900 psi. Okay, so theoretically, we could go ahead and stay in this position. It's going to stay at 900 psi, and additionally, we could go back to the closed center position, and theoretically, if we were to put a pressure relief valve right here, even in the closed center position, In an ideal world where there's no leaks, we should also see 900 psi, and it's going to hold it there. Because again, fluids are incompressible mediums, and that's not going to move. It's basically statically held in that position. Okay, now we want to go ahead and retract our load. What's going to happen? We're going to go ahead and move ourselves to the cross-connected position where pressurized flow enters this end, the rod end, and it can dump the cap end flow to the tank. And at this point, basically, our cylinder starts to retract because this is, at this point, it's a confined area and pressure is going to start rising and rising and rising, and it's going to act on the rod end face, which we know has got this tiny area subtracted because the rod's in there. So now again, it's the same load. It's the same load. And that was the area of the cap. Here's the area of the rod end, but less area. So what do you think the pressure requirement is going to be? It's again, same weight, less area. So obviously the pressure has got to rise to a greater value to retract the same load. Okay? So pressure rises and rises, rises up until the 4,000 pounds of force is generated, and the cylinder retracts. And now it's reached the limits of its travel, and this pressure in here continues to rise until it reaches the pressure relief valve setting, and it dumps P to T. Okay, so you may have never even touched a hydraulic system before, but just by looking at the schematics, you know what this thing does. Okay, and in theory, we could go ahead and put this back into our closed position, and if we had our pressure relief valve right there, excuse me, pressure gauge right there, that would still read 900 psi. We know that's not the truth because there is going to be leaking across that valve. Okay, but now that we've discussed not only the symbols and the major question, what does it do? Let's actually throw some numbers in here. So we already said it's a 4,000 pound weight. It's moving 24 inches. Let's say we've got a cylinder with a barrel diameter of 3.5 inches. Let's say the rod is 1.5 inches. Okay, our pump produces a flow of 4 gallons per minute. Okay, so now we want to figure out the pressure at extension, pressure at retraction. We want to find the extension speed, retraction speed, the work on extension, work on retraction, power, extension, retraction. This is the whole kitchen sink problem here. And let's see, what else are we going to do? We're going to have some discussion about pressure while we do this here. I think that's it for now. Let's start for pressure of extension. Okay, so pressure for extension is, we're going to figure out the area of that cap end. So I said it's a 3.5 inch barrel. So the area for the cap, pi over 4. Let's just do the formula. D squared. When D is 3.5, pi over 4, 3.5 inches squared should give us an area 9.621 inches squared. So force PA, that's our Pascal's law. We know the force, 4,000 pounds. We know the area, 9.621. Force divided by area should give us pressure. 4,000 divided by 9.621 inches squared pounds. You don't have to put the units in there in those formulas, but and it may actually sometimes confuse the issue. But keep track of the units. Let's put it that way. So 4,000 pounds divided by 9.621 inches squared. It's going to be 415 pounds per square inch. So basically, as this pump in the straight through position, the pressure, so basically the pump is going to provide flow, and the pressure is going to rise from 0 to 10 to 15, and basically the load is just going to sit there until it reaches 415 psi, at which point the cylinder is going to extend, and it's going to stay at 415 psi while the load is extending until it reaches the limits of its travel, and then becomes basically a confined space again that's not moving, and pressure will rise and rise and rise until the pressure relief valve, in this case, was set at 900 psi, dumps. Okay? So let us figure out the pressure for retraction. Okay, pressure for retraction, again, look at this diagram here, less area, so you think it's going to be more pressure. So let's figure out the area of the rod end. The area of the rod end is the area of the cap minus the area of the rod. We already figured out the area of the cap. What's the area of the rod? Pi over 4 d squared. What is that d? Well, we said rod diameter, 1.5 inches, minus pi over 4, 1.5 inches squared. We already had 9.621. 9.621 minus 1.77 inches squared. Going to give us an area of 7.854 inches squared. What is the pressure required to move 4,000 pounds with an area of 7.854 inches squared? Again, using our Pascal's law, force divided by area, 4,000 pounds divided by 7.854 inches squared is going to give us a pressure of 509 psi. Makes sense. Less area, so the pressure needs to rise to a greater value to move the same load. Okay? So we already figured out pressure at extension, pressure at retraction. Let's go ahead and skip to right to work extension and work retraction. Okay, so what is work? Work, or energy, is a force applied over a distance. Okay, so force applied over a distance, F times D. So pounds times feet. If we move 4,000 pounds 2 feet, or 24 inches, for extension, 8,000 foot-pounds of work on extension. So if we move 4,000 pounds 2 feet on retraction, how much work have we done? There's absolutely no need to go through the same formula again, because we did the same load, the same distance. 8,000 foot-pounds of work. Check, check. So power extension, power retraction. Do we have everything we need for this? The answer is no. First off, what is power? Power is the time rate of work. Okay? So the time rate of work, we need the time. So we need to find our extension speed at 4 gallons per minute and our retraction speed at 4 gallons per minute. Now think about this. First, the barrel, the cap end, has no rod in it. So it's a larger area to fill up. The rod end has a rod in the middle. It's a smaller area. And at that same 4 gallon per minute flow, if there's less volume, don't you think the retraction would be faster? And we'll find out if that's true or not. So just start thinking about these things right now. Okay, so let's figure out extension speed. Okay, if we've got a volume per time, i.e. a gallon per minute, and we're trying to figure out a certain volume, if there's a volume per second going into this, or unit of volume per time going into something of a certain size, what it makes sense is that volume, whatever it is, divided by the flow rate. That's what's commonly referred to as Q, that particular volume. So if our volume is in gallons and our flow rate Q is in, again, gallons per minute, this minute goes upstairs. So gallons divided by gallons per minute crosses out, you're left with a unit of time. So that's how you figure out extension speed. So if we know our flow rate Q is 4 gallons per minute, how long does it take to extend that cylinder if we know the area of this was 9.621 inches squared and it's 24 inches in length? Well, that's the formula we found out for our cylinder. So the volume for a cylinder is pi over 4d squared times h. That's really the area times h. So 9.621 inches squared times 24 inches should give us a volume 230.9 cubic inches. Okay, so not exactly the most convenient method, convenient unit. We typically use gallons. Luckily enough, a gallon is equivalent to 231 cubic inches. So that's roughly 1 gallon. It's like 0.969, something like that, gallons. 0.996 gallons. Roughly equivalent to 1 gallon. Okay? So how long, if this space is 1 gallon, how long will it take to fill up if 4 gallons per minute are going into it? Well, it's pretty obvious, 1/4 of a minute. Okay? So 1 gallon divided by 4 gallons per minute. So again, the gallons cross out, and you're left with a minute. So 1/4 of a minute, or 0.25 minutes, or 15 seconds, because 1 minute is equal to 60 seconds. Okay? So we just figured out the extension speed. It took 15 seconds to extend that cylinder 24 inches. So now we can figure out what the power requirement of that was. If we did 8,000 foot-pounds, power exerted, in 15 seconds, what is the power exerted on an extension? Well, 533 foot-pounds per second. What's that in horsepower? If 1 horsepower is equal to 550 foot-pounds per second, roughly equivalent to 0.969 horsepower. Okay? So now, let's figure out retraction speed. Same thing. 4 gallons per minute going into a fixed volume. Only this time, the volume is a cylindrical in shape with a cylindrical center removed. We can figure this out as the area of the rod end times the height of that cylinder, or if you want to be area of the cap times height minus area of the rod times height. So basically, two different ways to do it. Let's just go for this one because we already figured out the area of the rod end is 7.854 inches squared times a height also of 24 inches, because again, if it's fully retracted, it's traveled that entire same distance. So what do we get here? Should give us a value of 188.5 cubic inches. What's that in gallons? 1 gallon equal to 231 cubic inches, 0.816 gallons. How fast will a flow rate of 4 gallons per minute fill up a space of 0.816 gallons? 0.816 gallons, 4 gallons per minute. It's going to give us 0.204 minutes. Or, because a minute is equal to 60 seconds, 12.24 seconds. Okay, so we have confirmed the truth that a smaller space, because the rod is in the center, at the same flow rate of 4 gallons per minute, is going to retract this thing faster. Now again, the rod has taken off that space, so it's smaller area to move the same space means we need increased pressure to move it. And additionally, because it's a smaller space, at the same fixed flow rate, it retracts faster. Pretty cool, huh? So now, how much work have we exerted? Well, again, it's same weight, same distance, 4,000 pounds, a distance of 2 feet, 8,000 foot-pounds of work or energy. But let's figure out the power requirement, which is the time rate expenditure of energy, 8,000 foot-pounds per second, in 12.24 seconds, gives us a value of 653 foot-pounds per second, which, in comparison to our extension, is a lot bigger because we did it a lot faster. Okay? Let's convert that to horsepower. 1 horsepower is equal to 550 foot-pounds per second. Ultimately, 1.18 horsepower. Check, 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 check. Using everything we've learned in a systematic method, we figured out everything we needed, okay? So it helps to stay organized. The way I did this, you could do these things in different orders too. You can go ahead and figure out all your areas and all your volumes right from the get-go so you have those things working. I broke it up so that way we could see each individual step. You don't have to go through all the rigorous steps that I did. You can jump and skip steps, and that is okay with me. This is a little bit longer example because I was pretty arduous about it when you introduce it. Okay, speaking of short steps, let's talk about hydraulic horsepower. So we figured out on extension, we're roughly 1 horsepower. On retraction, we're 1.18 horsepower. There's a secret formula out there. If you know the pressure in pounds per inches squared, and you know the flow in gallons per minute, you divide it by this magic number, 1714. will give you the horsepower requirement. So let's take, for example, our extension. Our extension, well, we're always fixed at our 4 gallon per minute flow rate. What was our extension pressure? It was 4, where is it here? Extension pressure, 415 psi. PSI divided by 1714. 0.969 horsepower, which was what we got earlier, 0.969 horsepower. And some of you guys are like, whoa, how did he do that? Well, first off, it's this magic number here. I don't like using this formula because it's got some magic number that you are not going to remember. Okay, this is how you do it. Okay, if a pound, let's do it this way. So just think of the units. R, pressure, and flow rate, whatever those values might be. Pound, inches squared, we're taking the units over here. A gallon per minute. Well, a gallon per minute is actually 231 inches cubed in 60 seconds. So pound inches per second is what we're left with. Again, keep our numbers for P and Q here. Power is in foot-pounds per second. We got inch-pounds. 1 foot is equal to 12 inches. Whoops. So these guys cross out, but I remember you got to keep these numbers near. 231 divided by 60. So now we're left with 231 divided by 60. In this particular case is 12 foot-pounds per second times our original flow numbers. We're left with foot-pounds per second, which is a unit of power. But our formula gives us our value in horsepower. So we got to go ahead and convert that. P times Q, 231 divided by 60 times 12. What is 1 horsepower? 1 horsepower is equal to 550 foot-pounds per second. These guys cross out, cross out. P times Q, 231, 60 times 12 times 550. Horsepower. What's this number? P, Q, 1714. Okay? So this is a shortcut formula. If you know the units, you don't have to remember 1714. If you use it enough, you're just going to remember it. So let's do that on retraction. We were fixed at a flow rate, 4 gallons per minute. 1714. What was our retraction pressure? 509 psi. What do we get? 1.18 horsepower. That is, if you have pressure gauges and flow meters, you can do that shortcut. Otherwise, you have to go ahead and figure out extension, retraction, speeds, extension and retraction, work, extension and retraction, power, extension and retraction. Okay, let's have a further discussion about pressure here. And that's where we're going to end this particular examples here. So pressure. We determined that our retraction pressure was 509 psi. That means basically it's 509 psi above atmospheric pressure. So whether you know it or not, there is a lot of air on top of you when you're standing on the earth, and it's pressing down on you with a force of 14.7 psi. So this column of air, I don't know how many miles thick it is pressing down on your head, or well, every square inch on top of your head, with a pressure of 14.7 psi. That's atmospheric. So the pressure that we read on those gauges is pressure above atmospheric, and that should technically be known as psi G, which is gauge pressure. It's pressure above atmospheric. If you see someone write psi without the G, they typically mean gauge pressure. This is in contrast to psi A, which is absolute. Absolute means include atmospheric pressure. So if here is 0 psi A, basically meaning a absolute vacuum, and here is 14.7 psi A absolute, that's atmospheric pressure. Gauge pressure is anything above that. So if I said 509 psi G, or just psi, I'm implying that it is 14.7 psi above absolute. So what is our absolute pressure in this case? Well, psi G plus atmospheric pressure is equal to psi A. So in this particular case, 509 plus 14.7 523 psi A absolute. So there's a difference. What's the difference? Atmosphere. Absolute pressure is always 14.7 psi higher than gauge. And that 14.7 psi varies where you are on the globe, whether you're on the mountains or down at sea level. But typically it's 14.7 psi. So there's something out there called a bar. A bar, if you can think about it, is a unit of pressure, and it's roughly equivalent to 1 atmosphere of pressure. Okay, so if 1 atmosphere is 14.7 psi, 1 bar is equal to 14.5 psi. And the bar is a unit of pressure. So if 1 bar is equal to 14.7 psi, and I have a gauge pressure of 509 psi, what is that pressure in bars? Well, do our unit conversion. What do we want on the top? 1 bar divided by 14.5 psi. What we don't want on the bottom, these guys cross out, and we get a pressure of 35.1 bars. Basically 35 times roughly the atmospheric pressure. So the bar is a neat unit because it also serves as a bridge unit between the English system and the SI system. The SI unit for pressure is, again, so English unit, 1 pound per square inch. Same thing in SI, 1 newton of force on 1 meter squared. I mean, think about how big a meter is. And if there's 1 newton of force on it, which is a tiny amount of force on a big, big area, substantially less, it's a weaker unit of pressure. And that weaker unit of pressure, 1 newton per meter squared, is a Pascal. So if it's a weaker unit of pressure, you've got to, it's not convenient. So a more convenient unit is the kilopascal, 1,000 pascals. So the point of this thing is a bridge unit. 1 bar is roughly equivalent to 100 kilopascals. Okay, so if someone gives me a pressure of 509 psi, and I know that means 35.1 bars, what is that pressure in the SI system? Well, 1 bar is equal to 100 kilopascals. .351 kilopascals. Okay, so it's just a convenient bridge unit. You're typically going to see bars on a scale. On a pressure gauge, here's a PSI scale, 14.7. Let's say roughly 29. And that's in a black numbers or whatever number. Scale right next to it, maybe in red numbers, 1 bar, 2 bars, so on and so forth. Okay, so that needle is pointing at the same value, and you can read it PSI scale or bar scale, or maybe you got one of these guys with 3 scales, you've got 100 kPa. And what I've just drawn there is a board-on-tube gauge. Sometimes they're liquid dampened, sometimes they're air. But if you peel this face off, here's this needle with a scale on it. If you peel the face off, what's behind it, you'll see it in lab because I've got one torn apart, is this tube. It's a fluid-filled tube, and as the pressure increases inside it, it forces it outward to kind of uncurl, and that uncurling action is hooked to this mechanical linkage with the needle on it. And so the needle is hooked to this mechanical linkage right here. And as that thing uncurls this direction, it's going to force that needle up in proportion to how much it uncurls. So as pressure rises on this particular end, the needle will deflect in this manner. So I'm going to go ahead and show you guys that in lab. Okay, this is enough for this portion here. Basically, this is acting as a summary of all the concepts we've learned thus far.